So what's the take home? 1 subdifferential is a set. 2 subdifferential is a convex set. 3 subdifferential is a closed set. 4 subdifferential exists if you are talking about in interior. 5, if f is differentiable or differentiable at x, then subgradient or subdifferential of f at x reduced to normal gradient. This is the most powerful thing. It says, okay, subgradient is more general than gradient. Because when you have differentiability, you are subset of me, something like that, okay? So how to prove it? Actually very easy. So, f is differentiable, then Frechet-Gartov directional derivative exists at this, okay? Then what is subgradient? But this, okay, don't forget 1 and 2 are different things, okay? 1 is derivative, 2 is subgradient, okay? So I have 1 and 2, then now what? Here's the funny part, both of them have this guy. So, green equal to this long green larger than this. So, horizontal line larger than curved line. Horizontal line larger than curved line. Then what's next? Q. Okay, right? What is this O term? This O term go to 0 because this O term go to 0 faster than everybody else. So when I take limit y go to x, this can go to 0. So this line is for all y. Now if I put this term disappear. I have this. This g go to here. I have this. That means what? That means I have a funny thing. This thing I call u. This thing I call v. I have this for all v. This is important. This implies u is 0. Okay, it's a fact. Why? Because this is for all v. If some part of u is positive, I can make a v that part is, so let's talk about it. So u1, u2, okay, v1, v2. I have this, right? If this part is positive, because this is free for any number, I can choose this is -3, then this is false. Or I can choose this is -3 million, then this is false. Because don't forget this is for any v. So if inner product is true, larger than 0 for any v, then this guy must be 0. This guy must be 0, that means f minus g is 0. That means g is gradient f. And here, important thing, this part is a particular subgradient. So if I write the subdifferential, it will be what? It will be, what is this? This is a set. So this line is not one inequality. Infinitely many inequality. What is this? This is one special case of this infinitely many inequality. And now 2 is true will lead to this is true. So in other words, any subgradient here will go to here, and therefore if f is differentiable, we only have one thing, and that's the gradient. That's the proof. Yes. So that means what? That means this is the why. If you have differentiation, the classical gradient come up. And the only requirement is you need this guy to be true, which what? Directional derivative, Frechet derivative, okay? That's it. And this is funny. This is saying if f is differentiable, then you have this. Actually, you can also have the opposite. If you can show that the subgradient only have one element, then f is differentiable. So in other words, it is totally possible to develop view analysis starting from convexity. Because this guy have nothing to do with differentiation. You can start with some definition of convex set and then build this and then use it to prove differentiability and then develop all the other things. Yes, this is funny. Then this one is very long, I skip, okay. And then this naturally boils down to this funny thing is what the heck is convex function to do with differentiation? This is the idea. Convex function and non-convex function are very different. You probably know there are continuous function that is nowhere differentiable. That means there is a function continuous everywhere, but everywhere non-differentiable. It's the Weierstrass function, that kind of fractal function, okay? But first of all, is this convex? No, right? I just show you something like this. But if we have convex, here's a funny thing. This is impossible. So if we have convex function, it cannot be crazy. It cannot be crazy. Convex function is differentiable everywhere. This is detail, but I'm not going to talk about detail. In fact, Rockefeller proved that in terms of measure theory, non-differentiable point for convex function have measure 0. That means non-differentiable point for convex function almost doesn't exist. And that's true. What is the non-differentiable function? This. What's the non-differentiable point here? Classical non-differentiable point here. What's the measure here? 0. Okay, let's say I have another convex function. Non-differentiable, non-differentiable, non-differentiable. What's the measure? 0. Let's talk about how do we compute subgradient. So first, I already showed you 2 examples. What's the subgradient of absolute value? This thing. When x is 0, you have a set. What's the subgradient of this thing? This thing. When x is 0, you have a set. Lastly, what's the subgradient of the largest eigenvalue? I have a function f takes in an input x is a Rn by n matrix. Let's say have eigenvalue, okay, make it simple. And let's make it symmetric, okay, anyway. And then I give a number. And what is this? I want the largest eigenvalue of x. Now I want to find the gradient of this thing. Okay, this does not exist, so we have to talk about this. Because this is convex, so I can talk about this. Now, how will we find the gradient of eigenvalue? Now things start to become interesting. So I have this, okay, I make a mistake here, this n should go to here. It's positive definite square matrix, blah blah blah, okay, symmetric, okay. And then, okay, recall we're now in matrix, so this is matrix form, okay. This is the largest eigenvalue, v1 is the largest eigenvector. I'm going to tell you, the largest eigenvector v1, this is the column vector, multiply the transpose, your largest eigenvector transpose, this gives you a rank 1 matrix. This rank 1 matrix is the slope of eigenvalue. So, what's subgradient? This is definition of subgradient, right? Fy larger than fx plus something y minus x, just to find a something. What's the something? So, what's the lambda function? Definition. Any v smaller than 1 yvv is the largest eigenvalue. I want this, so I create x, y at x minus x. I have this. Then what? Norm is linear. I can split them easily. Soup these two things, okay, nothing happened, but for this guy, v can go out, so this part is a little bit tricky, but it's the same. I have a, x, b, so you know that I have these, right? But I can also throw the x to the other side, so I have a, this. So now this is what? This is vector inner product. This is now matrix inner product, because this is the matrix, and this becomes trace. But anyway, so I just throw the x, no, v to the other side. Now I have this. What is this thing? This thing is exactly eigenvalue of x. So this thing is this thing. Yeah, done. So what's how do you differentiate eigenvalue? This is how you differentiate eigenvalue. Here's a thing. Can we do this for the second eigenvalue? I'm sorry, no, because second eigenvalue is not complex. So we cannot do that. Okay, now second example. This, what is this? I have a bunch of linear functions, and then I max them. What is the subgradient? It will be convex combination of ai. If my function is 3x minus plus 7, negative 4x plus 16, 5x plus 5, and then of them max, what does it look like? It will be something that this is the first line, this is the second line, this is the third line. What's the max of this thing? The max of this thing will be the red thing, right? What's the subgradient of this thing? So first, subgradient of this point, easy. Subgradient of this point, easy. What about subgradient of this point? It will be this line, this one, the slope, and this one, the slope, convex combination. That means what I told you previously, right? So this is what I told you geometrically. Now let's see how do we prove this. So y is what? Max of this thing. So I put a y here. So this x is y, so I have a y here. And then what? This is max on all the ai. So if I just go to a particular I, not the largest I, then of course I have larger than. Then now I have this. Now we're the same trick. I just try to create something that looks like this up here. I have y, I make an xx linear, split them. What is this part? Is fx. This fx is important. This fx is true if this ai is really the largest j here. So now I have this thing. So that means fy larger than fx plus this. But this I have to be the index I that makes this is true. So therefore I have this. So done. And since this is a convex set, do you remember? Subdifferential is a convex set. So I can even take convex combination is still a convex set. So I take convex out. So it makes this picture. If I'm just saying the I that is the arc mean of the fx, then I'm saying one vector. But if I take convex out, I have this region. This is the picture I told you, right? So that's the idea. This is the idea. This is what I said. Subdifferential convex set, so I can take convex out. So these are two examples. I do eigenvalue. I do max. So in other words, what are you trying to do? You try to create this is true. Then the thing here will be subgradient. And this can be anything as long as it's convex function. So it's an elliptic operator convex. You need to prove elliptic operator convex, then you do this. And then whatever crazy thing, as long as it's convex, then done. Don't forget, convexity is a geometry idea, it's not an analysis idea. It can be algebra. If you have an algebra thing that is convex, then this will be true. Okay? And then now let's talk about the calculus. That means the rule. These are the rule, okay? And these are formula. And because of time, no time to prove this formula. If I have f multiply a, alpha, then my, subgradient, I don't care about alpha. Important, alpha needs to be larger than 0. Because I have AP graph. If my alpha is negative, I flip my AP graph, then I don't have the support. This idea. And then what about this? Subgradient now is Minkowski sum. Because AP graph. What about this? What about this point? If F2 is differentiable, because F2 is differentiable, we have singleton. It's just gradient. Then Minkowski sum is just a set plus a point. So it's basically shifting a whole set by a single point. So I have this. And what happens if I have a constant? Constant is a F2 with 0 gradient. So basically it's a Minkowski sum with my set plus nothing. Minkowski sum of this is just the Minkowski sum, is just this alone. Yeah. And what about this? Okay, I have proved you using the A plus X plus H in the cutoff of Frechet. I forgot, then it's the same. Yes. What are the things that is complicated? Is these two. In general, you don't have equality. You have, because these are sets, so you have subset. And this become equal is a theorem called Moore-Rockefeller theorem. That is, if the interior of the two functions intersect, then you have equality. And lastly, you have this max. I just use it to show you. This generalized to this version. Okay, it's a generalization of 8.2.16. That means this one. Okay, and these are the calculus. And now I have two different things because we have what? We have a set of a G. So if you do the calculation, this is what? This example, I give you the whole G. These are all the G. This is called strong subgradient calculus. This example, I give you one G. So this is not strong, this is weak. So this is the idea. Weak means you find one particular subgradient. Strong means you find all the possible subgradient. For optimization algorithm, you only need one subgradient, so weak is enough. But if you talk about optimality condition, you need to show that my F is the best among all the possible subgradient, then you need strong. That's the idea. And then again, this is monotone. That means what? I have this. This is convexity. But now I change to subgradient version. Okay? I have this. And then this is the duality thing. Okay, we don't talk about duality, yes or no. And then here are summary. Okay, so we have this. It's continuous, it's closed, it's convex set, it's non-empty if I'm in the strict interior or relative interior, and if differentiable I'm singleton. Now, how do we compute subgradient? Okay, I just show you example by this. What about the other way? You can do this by limit. Limit is you build a limit, okay? Or you do duality. This is the one I showed you last week on the subdifferential of norm. You need to know something called conjugate, but not yet, okay? And lastly, before I finish, what the heck is subgradient useful for? Is this. Now we have the optimality condition, and this will naturally give you KKT, a lot of crazy optimality condition, is that I minimize Fx. This is very general, important. I just said F is convex. I didn't say F is differentiable. I didn't say F is only one part. F can have many parts. One part is the fitting in the machine learning, other part is constraint. So this is saying that I minimize Fx as long as F is convex. X star is a solution if 0 belongs to the subgradient at X star. And how to prove it? Actually, it's just crazily short. This is convexity, right? This holds for minimizer. So I replace this X by X star, then I have this. X star by definition is what? X star by definition is X star smaller than any F, other F. So it's smaller than any Fy. If this is true, I have to what? This G need to be 0. So therefore 0 belongs to a subgradient. And this is an idea. This function is not differentiable at this point, but 0 is a subgradient. This point can have more than one subgradient, but 0 has to be one of the subgradient. And you recall, if F is differentiable, subgradient reduced to one single element, then we get this back. And furthermore, you remember we have constraint, then it said we have the normal constraint. The negative gradient need to be the normal constraint, right? It actually exactly this. Why? Because suppose my F is H plus indicator function of a C. So now the constraint. So when I do this, and now let me tell you, this is what this is. So subdifferential of indicator function is normal con. So I move this. So that means what? That means this is the most general. You can use it to derive KKT. Yeah, so what is KKT? Mean F subject to Gx is 0, Hx larger than 0, something like this, right? What you do, you put everything up to here into a big F. So now I have a big F. All the FGH are here. So I want to minimize F, and I want to minimize the indicator function that G has to be 0 of G, and I also want to minimize the indicator function that H has to be larger than 0. I have three parts. What's the optimal condition? 0 belongs to subdifferential of this big thing. Break this thing into small parts, put it to the analysis, you get KKT. So that's why subgradient is so powerful. And now we have finished subgradient. Then this is another example. We have this proximal operator, and that's why we talk about subgradient, because we need this for the optimality. What's proximal operator? The smoothing, the Moore envelope for the L1 norm. Okay. Then what is the optimality of this? Is if X star is the solution of this thing, the variable is C, the input is X. Then what? 0 belongs to the subgradient of this, subgradient of the whole thing. Okay. I can split them because this is now singleton. I don't need to worry about crazy addition. Now I apply a plus. I have this gradient, you know how to differentiate. So this is just X star minus X. I have this. So I have this expression. What is the expression? It's saying that then it will give me our output X star, right? How do I know this is correct? What is this? This point belongs to this thing. This point plus the subgradient of F exactly at this. Don't forget, this is a set. So there are more than one thing. So this is belong to. The last line is functional analysis, which is you just treat as random. So now plus partial f. Now I do a crazy action. I treat them as operator algebra. I can do it like this. Something minus 1, cancel out the bracket. Then this one's gone. Now I get this. So what is this? Resolvent in PDE or in functional analysis. So in other words, what the heck is this thing? This exactly is how you calculate the x star. So in other words, I have an x as an input of this thing. How do I get x star? You do this operation. And this is tomorrow. This will be, okay, finally, we can talk about how do we solve this gradient descent. Okay, now I have this part. Oh no, I don't know how to do. Okay, what I'm going to do is I do proximal gradient descent. Gradient descent, nothing new. And I prox this thing on this thing. So it is this thing, I call it z. This whole thing is z. So now I prox this thing, okay, add the L2 norm in your f, okay. So because it's infinite convolution, so now I have arc mean on theta, okay. What? This is my function. So the L2 norm of the difference, what's the L2 norm? Is z minus theta, okay. So I want to solve this. This will be the solution of my update. So if I can somehow get an expression here, I solve this using gradient descent. In one iteration, not in one iteration. That means I run this many times, I update this. Then the question will be, how do I know this is a solution? So therefore, x star is a solution, partial derivative, not subgradient. This thing subgradient plus this thing normal gradient. So in other words, what's the solution? The solution is if my x fulfill this funny implicit x equation, then I get the solution. So the answer is, okay, because of time, I'll talk about this tomorrow. X star is called a soft holding of z. In other words, it will be something like this. This is my z, y equals z. This thing is funny. My z, so this whole thing, the x star will be what? If my z is too big, I move it down. So it will be z minus lambda if z larger than lambda. If z is smaller than negative lambda, I move it up. So z plus lambda if z is smaller than negative lambda. Everything else in the middle is 0. And what does it mean? How do you minimize this thing? It will be, you do a gradient step, you have this funny z, you do this funny thing, then this is a gradient update for this. And this is because of subgradient.